Hi everyone, I'm Dr. Josh Redstone and I'm back with another video lecture for my class Phil 2501A, Intro to Philosophy of Mind. And today I thought I would talk about artificial minds, because we haven't really spent too much time talking about this sort of thing in class, and I thought it would be a nice way to end things off. So today's lecture is actually the first part of a two-part lecture. Today we'll be talking about some of the background materials that will be helpful for you to understand things like artificial minds, artificial intelligence, and that kind of thing. We'll cover a lot of the theoretical background there today. And on the next lecture, I'm going to move on and talk about the prospect of artificial consciousness and try to differentiate between artificial consciousness and artificial intelligence. So let's begin today by talking about artificial intelligence. Now, there's a few key terms that I think you'll want to keep in mind throughout this lecture. Terms, well, not just terms, but fundamental concepts that are important when it comes to AI. And four of the big ones are representations, and in particular mental representations, artificial intelligence itself and what that term actually means, and machine learning. So I'll talk about each of those in their turn before we get going. So representation, well, when philosophers or cognitive scientists talk about a representation, they're talking about a way or a means of representing information. When it comes to AI, computer science and those kinds of things, these are usually some kind of symbol, although as we'll see, not always. And the kinds of symbols I have in mind here are digits like 0 and 1, which of course can represent values like true and false, or on or off. And all of this goes back to some of the fundamentals in information theory, especially the work of Claude Shannon, who I actually talked about recently in an online lecture for my other class, Phil 1301B. Basically, Shannon showed that we can represent any logical or mathematical relation in binary, and we can also use electrical circuits to implement a symbolic binary computer language, what we would call machine code today, I suppose. So, when we talk about a representation in the context of artificial intelligence, we're talking about representing information, usually with a symbol or a set of symbols, but as we'll see, not always. Of course, a mental representation is mentally stored information. So it's information, it could be about the world, it could be about the organism itself, or it could even be about other representations in the organism's mind. So a representation of another representation like that is called a meta-representation. But in any case, mental representations are simply mentally stored representations or mentally stored information. And that information could be about any number of things: the environment, the organism itself, or the contents of the organism's own mind. And again, how this information is actually represented when it comes to human beings is still not agreed upon. Some thinkers like Jerry Fodor think that we represent and process information in a symbolic language called the language of thought, or mentalese. And other thinkers think that human cognition is subserved by something that's more like a neural network, which, as we'll see, doesn't use the same kinds of representations as more traditional varieties of artificial intelligence like digital computers. So we'll talk a little bit about this stuff in this lecture and in the next lecture, but I just want you to be aware of these fundamental concepts. Another important concept, of course, the main one for today, is artificial intelligence. By artificial intelligence, we don't mean that we're creating some kind of fake or cheap copy of human intelligence, although that may be how many artificial intelligence applications certainly seem to some of you. But by artificial intelligence or AI, what we mean is creating a cognitive system, a human-made cognitive system that could deal with the same kinds of problems, solve the same kinds of problems, demonstrate intelligent behavior, similar to the way that we do. And some thinkers distinguish between strong AI on the one hand and weak AI on the other hand. So weak AI is the kind of AI that's focused within a limited domain. It relies heavily on human assistance or the work of the human programmer to do what it needs to do. And some thinkers would say that it merely simulates human performance in a certain domain, but isn't really intelligent on its own. And this is something we'll probably get to a much greater extent in the second lecture on artificial consciousness. But you could think of something like a chess-playing computer program as weak AI, if you like. I mean, it only does one thing, right? It only plays chess. And if you try to get it to do something else, it just won't work, right? So that's weak AI. It's domain specific, quite limited, and relies heavily on assistance from humans or the work of the human programmer. Strong AI, on the other hand, is not as focused. It's general, so it's domain general. That is to say, it's domain general. It wouldn't rely on humans to do what it does to any great extent, and people would agree that it is truly intelligent and thinks for itself. Of course, different thinkers will think of strong and weak AI in different terms. And whenever a new artificial intelligence application comes out, which maybe previously might have been thought of as a strong AI, boy, if we had a computer that could do X, that would count as strong AI. And then we create a computer or a computer program that can do X, and once it's been around for a little while, it doesn't seem very impressive anymore. Perhaps 40 or 50 years ago, computer scientists would have thought that a computer that could understand what you're telling it, a computer that could engage in natural language processing would be strong AI. Of course, nowadays we have that kind of AI all over the place. My phone, together with the cloud, the computing power of the cloud, can listen to what I'm saying and understand it. But that's so ubiquitous now that we don't think it's very impressive. So a lot of AI, tends to be regarded this way, with a lot of ooh and ah when it's still hypothetical, and then when it becomes a reality, it's maybe not as regarded as very impressive anymore. So that's strong and weak AI, and we'll continue talking about that as we proceed through this lecture. Another important concept to keep in mind is that of machine learning, and this is basically machines learning to do things rather than being programmed or told specifically how to do things. We're not going to talk about this in too much detail today, but again, it's an important concept to be aware of, and we will encounter it today in a sort of peripheral manner, just here and there, as we cover some of the fundamentals of artificial intelligence. All right, so let's get started. Okay, so let's begin by talking about what computation is. And to do that, we're going to go all the way back and look at the work of Alan Turing, who was a very influential early computer scientist. Indeed, some say the first real proper computer scientist. And he's also considered the forefather of artificial intelligence. So what Alan Turing did for computer science, AI, and for cognitive science and philosophy of mind in general was formalize the notion of computation. Indeed, a lot of people think that, computation in a nutshell is what computers do, right? We haven't talked about what computation is yet, but computation is what modern day digital computers do. And according to many people, computation is also what minds do, artificial minds and human minds. So that's pretty interesting. But how did Turing formalize this notion of computation? Well, he did so using a mathematical machine, an imaginary mathematical machine, which has come to be known as a Turing machine. He conceived of this machine to address a problem that computer scientists at the time we're facing called the halting problem or the decision problem. And that problem, or basically the problem in a nutshell is this. It's the problem of determining whether, given a certain computer program and a certain set of inputs and so on and so forth, whether the program is defined for a particular set of inputs or set of outputs. We could also rephrase this as the problem of working out whether there's some procedure that we can apply to see if a math or a logic problem, say, has a solution. So a solution to the halting problem would be like a simple step-by-step procedure that you could apply to see whether a computer program is defined for a certain set of inputs and whether it will eventually deliver a solution to the problem you put to it, or whether it's not defined for those inputs and will just continue looping on in a futile effort to arrive at a solution. So to help tackle this problem, Turing had to formalize the notion of computation. And to help him do that, he borrowed a very, very old notion, the notion of the algorithm. This goes all the way back to the Islamic Golden Age, to a thinker named, and I'm probably pronouncing this wrong, Al-Khwarizmi. That's the figure after whom the term algorithm is named. And basically, Al-Khwarizmi was the first person to conceive of an algorithm, or what we now call an algorithm, and it was a set of step-by-step instructions for solving problems. Before that, in mathematics, a lot of instructions for solving problems were specific to each particular problem, but Al-Khwarizmi came along and said, we can just come up with these sorts of sets of instructions or recipes that apply to just certain kinds of problems, and it doesn't matter what the particular numbers we're pumping into these formulae are, right? So that's an algorithm, and Turing used this notion to help formalize computation. Now for Turing, what an algorithm is a set of unambiguous rules that we can apply to a problem, or a set of objects within that problem, to transform it into another set of problems in a definite and circumscribed way, to go from an initial state to a solution state in a definite, circumscribed way. So, with this notion of the algorithm that Turing borrowed from these old mathematical thinkers from the Islamic Golden Age, Turing came up with this imaginary machine, a type of discrete state machine, called a Turing machine. It's a discrete state machine because it can only be in one state at a time, just like the digital computers of Turing's day and just like the digital computers today. They can be in one state at a time. And a Turing machine features an infinitely long tape that has cells on it, a bit like the tape from a VHS tape, if anyone remembers those. It has a machine head, which it can use to move the tape one cell to the left or to the right. It can write symbols on the tape, it can delete symbols on the tape, and so on and so forth. It has a window, a display window, so that the operator of the Turing machine, were we to build one, can see what's going on. He or she can read the state of the machine and so forth. And it has a machine table, which contains all of the instructions for the Turing machine to solve the problem that it's meant to solve. This is what we would call a computer program today. So remember, these machines are imaginary, but their behavior is determined by the current state of the machine table, the instructions in the table more specifically, and the symbols that are on the cells of the tape. And all of this, each discrete state that the machine could be in, could be represented mathematically as sequences of numbers. And so even though Alan Turing never built a Turing machine, he was able to specify hypothetical Turing machines, say for solving particular arithmetic problems or logic problems or whatever, even playing chess. And because you could represent these imaginary machines numerically, Turing was able to generate mathematical proofs about the nature of Turing machines. Turing proved, incidentally, that there's no solution to the halting problem. So there's no way that we can come up with a solution that will tell us whether a program is defined for certain inputs and not others. There is no simple solution to that. He also helped articulate the Church-Turing thesis, and this is named after Turing as well as Alonzo Church, who was a logician and also Alan Turing's doctoral supervisor. They showed that any mathematical problem that can be solved algorithmically can also be solved by a Turing machine. So any computable numbers can be computed by a Turing machine. Lastly, Turing also showed that there's a special kind of Turing machine called a universal Turing machine, and a universal Turing machine could run any specialized Turing machine on it. So say I had invented a Turing machine that could compute, do some kind of mathematical computations like addition and subtraction. Perhaps I had a different Turing machine that could do multiplication and division. Well, a universal Turing machine could run both of those specific Turing machines. So that's a universal Turing machine. And the idea of a universal Turing machine depends to a great extent upon the Church-Turing thesis. And if the Church-Turing thesis is right, that essentially means that modern machines like this smartphone or even this laptop that I'm using right here are basically just universal Turing machines. So modern computers, if the Church-Turing thesis is right, are universal Turing machines. Now, Turing's work is very important because it provided the basis for understanding not only what computation is, but also understanding cognition or thinking as computation. So computation for Turing is all about transforming representations, information represented perhaps symbolically in this case, but not necessarily in all other cases, transforming representations into other representations, transforming inputs into outputs, that kind of thing, according to algorithms, according to definite circumscribed rules. So that's what computation is for Turing. And this is actually not in the slides, but I think it bears a mention. A lot of people, a lot of cognitive scientists, and a good deal of philosophers also believe that computation is what minds do. So cognition is just computation. It's just the rule-governed transformation of symbols. I don't think Turing himself even realized the significance of this work, which I'll probably talk about in our next lecture when we talk about the Turing test. But in any case, for now, Turing's work is very important because it gave people a way of formalizing the notion of computation as information processing. And if these earlier mentioned cognitive scientists and philosophers are correct, well, cognition is the same thing. Cognition is a kind of computation or information processing. And this, by the way, is called the computational representational theory of mind. But Turing's work is not the whole story. So let's turn to the work of Alan Newell and Herbert Simon to see where we go from here. So we've already had a quick look at how information can be represented, at least in the cases of Turing machines, and how that information, those representations can be transformed into other representations, that is via algorithmic information processing. And all of this is nicely captured by something that's called the physical symbol system hypothesis. Now, the physical symbol system hypothesis is an idea that comes down to us from computer scientists Alan Newell and Herbert Simon, who were working in the 40s and 50s, a little bit after Turing. Now, the physical symbol system hypothesis is actually making a pretty strong claim about not just physical systems, but what general intelligent action amounts to. And the physical symbol system goes like this. It says that a physical symbol system has the necessary and sufficient means for general intelligent action. So why is that a strong claim? Well, it's a necessity and sufficiency claim. For those who may not be familiar, necessity in logic goes a little something like this. We can say that A is necessary for B, where B could not be the case unless A is the case. So being a fruit is a necessary condition for being an apple. right? Whatever else is the case, you cannot be an apple if you are not first a fruit, right? So being an apple is necessary to be a fruit. So that's necessity. Sufficiency, well, we could think of that like x is sufficient for y, when knowing that x is true, or that x is the case, is adequate grounds to conclude that y is the case. So knowing, for example, that Elizabeth II is a queen, namely the Queen of the United Kingdom, is sufficient to conclude that she's female. So that's necessity and sufficiency, just quick examples if you're not familiar with those concepts. So the necessity and sufficiency claims of the physical symbol system hypothesis boil down to the following. The necessity claim says that nothing is capable of intelligent action unless it's a physical symbol system. So that's a pretty strong claim. And the sufficiency claim boils down to basically there being no obstacle to developing an intelligent system, a system capable of what Newell and Simon call general intelligent action, as long as it's a physical symbol system. So this is a very strong claim going on here in the physical symbol system hypothesis. But hang on, what is a physical symbol system? Well, this is how Newell and Simon characterized it. It has 4 key characteristics. The first is that it has symbols, and these symbols are physical patterns. So think here of the cells on the tape of a Turing machine with symbols written on the cells. Those are physical patterns, and those patterns represent information. Or think of zeros and ones used in binary. Those represent values like true and false, which are just electrical circuits that are on or off. And those represent, those circuits just being on or off represent values like true or false, or 0 and 1. So those are symbols, physical patterns. These symbols, this is the second characteristic, these symbols can be combined to form complex symbol structures that we call expressions. So we can put symbols together into longer strings of symbols to represent more complicated information with more complicated symbol structures. Thirdly, the symbol system contains processes for manipulating these complex symbol structures, that is, turning them from one symbol structure into another symbol structure. And finally, number 4, the processes for generating and transforming these symbol structures, that is, the rules, the algorithms, can themselves be represented by symbols and symbol structures in the system. So those are the 4 core characteristics of the physical symbol systems, or physical symbol systems. Sounds a lot like a digital computer, right? Well, digital computers are physical symbol systems, right? They use binary language to represent information, zeros and ones, which are just circuits that are on or off, so those are physical patterns. And if we were to actually build a Turing machine, perhaps it would look a little something like this here. If we were to actually build one, that would count as a physical symbol system too. And even the imaginary versions of Turing machines count as physical symbol systems, I suppose, albeit just an imaginary variety of them. So yeah, these symbols are just physical patterns, right, that represent information. The cells on a Turing machine are like this. The electrical circuits in a digital computer are like this. Even the symbols used in mathematical formulas or in formal languages like logic, like predicate logic, propositional logic, modal logic, all these different logical calculi. Those are all symbolic languages, so those are physical symbols, and these are the languages that physical symbol systems use for thinking. So that's it for symbols, but let's walk through the rest of the characteristics in a little bit more detail. These symbols, as I mentioned in characteristic number 2, can be combined to form more complex symbol structures, otherwise known as expressions. So if you think of the symbols and symbol structures as the alphabet, the letters in our alphabet, if you like, well, we can put our alphabet together and create words, if we like. And we can combine words to create more complex symbol structures, like sentences. These are the aforementioned expressions. So, we can group bits in binary into bytes. If a Turing machine has suitable instructions in its machine table, it can group symbols into longer expressions by using, certain specific symbols that delineate the beginnings and ends of more complicated symbol structures. Think of this as like the punctuation of our sentences that we're putting together. And whatever the system we're talking about, the rules, the algorithms in question that we're talking about, they're analogous to the grammar of our language, I suppose, if you want to think of it that way. So, now the core claim, remember the necessity and sufficiency claim of the physical symbol system hypothesis, is that intelligent action can be accomplished by the rule-governed transformation of symbol structures, and that any system that does this has the necessary and sufficient means for general intelligent action. So what did Newell and Simon mean by general intelligent action? Well, they mean something like problem solving. So, for Newell and Simon, there are lots of different things that count as thinking. Earlier I mentioned that thinking is information processing, cognition is information processing. But Newell and Simon are interested specifically in intelligent thinking. So that boils down to the ability to solve problems. In other words, it boils down to the ability to work out, given a range of options and certain constraints, which option will get you to the solution in the best way, or which option best satisfies the requirements and constraints of your problem. We can make this a little bit more concrete by considering the idea of a search space, or a problem space, as they're sometimes called. So a search space can be understood in terms of getting from an initial state to a goal state, right? And there are a certain number of permissible transformations within the state, or within this search space, that you can go through to get from the initial state to the goal state. And you can carry out these transformations in any particular order, by and large anyway. So if you want to think, for example, of a game of chess, right? A game of chess is like our problem space or search space, and the initial state is the starting position of each of the player's pieces, and any solution state where one of the player's kings is in checkmate will be a solution state. So any state where the opponent's king has been checkmated counts as a solution state. And the search space is all of the possible transformations. It's the set of all possible transformations from the initial state to a goal state. And for Newell and Simon, solving a problem is a matter of identifying the solution state and getting there through the search space. So any configuration of the chessboard where the opponent's king is in checkmate, working out the best one of those is, solving a problem partially. The other part involves working out how to get there through the search space. So we're not going to look at in too much detail at search spaces today, although perhaps if there's interest I could do another video on that later on, just for whoever might be interested. But the long and short of it is that solving a problem is a matter of traversing a search space in an optimal way, right? Now we can't just brute force every problem and search every possible route through the search space. That would take too much time. That would only work for simple problems. We could do that with a game of tic-tac-toe, for example, but we couldn't do it with chess. If we did that with a game of chess, our problem would become computationally intractable. For example, in a 1950 paper, Claude Shannon, the father of information theory, calculated that the number of possible chess positions in any given game is about 10 to the 43rd power. That's more possible chessboard configurations than there are stars in the observable universe. And checking those positions, say one position every second, would take an absolutely almost unfathomable amount of time to do. So that's what, that's an illustration of computational intractability, something that we can't solve in a reasonable amount of time because the problem space just gets too big. So brute force searching in chess is not very practical. So For complicated problems, you might use things like heuristic search, which is a matter of using kind of like rules of thumb to try and limit the search space. But in any case, we won't talk too much about that. That's probably best saved for another time. But in any case, that's kind of the long and short of physical symbol systems. Physical symbol systems have the necessary and sufficient means for general intelligent action. Pretty strong claim. And general intelligent action involves intelligent thinking or problem solving. Physical symbol systems have these four characteristics. They use symbols, which are physical patterns, to represent information. They can combine symbols into more complex symbol structures called expressions. Symbol structures are transformed according to rules. And finally, those rules for transforming and manipulating symbols and symbol structures can themselves be represented symbolically within the system. And this is all possible thanks to the foundations that Turing laid in the theory of computation. And it's also inspired a lot of research into, human cognition and thinking of what we do, what the human mind does in terms of information processing. So if this is right, if the computational representational theory of mind is correct, our minds are just naturally evolved computers. And there shouldn't be any barrier in principle to one day having strong AI, if this is all correct. So, that's it for physical symbol systems. But the physical symbol systems are not the only game in town. Let's move on now to talk about artificial neural networks. Alright, so physical symbol systems were inspired by digital computers, but artificial neural networks were inspired by brains and the way brains work. So first we'll take a look at single layer neural networks or single unit networks, and we'll finish off with a little bit of discussion about multi-layered neural networks. But before we get into all of that, it would probably be a good idea to just brush up on some of the biological details that have inspired artificial neural networks. So let's do that first. Now, the brain and the nervous system is composed of cells called neurons, and those cells consist of what's called a soma, or cell body, and that contains the nucleus of the cell. And they also have these hair-like extensions from the cell body that are called neurites. And there are two types of neurites. There are axons, which send signals. They terminate in an end bulb, and every neuron has one axon. And they also have many, many dendrites. Dendrites receive signals from other neurons. The connections between neurons, where a dendrite almost but not quite touches an end bulb from an axon, is called a synapse. And the neuron that sends the signal to another neuron is called a presynaptic neuron. A neuron that receives a signal from another neuron is called a postsynaptic neuron. Now, a single neuron can have inputs from lots of different other neurons, perhaps as many as 10,000 different neurons for a typical neuron. But for some neurons, they can receive inputs from as many as 50,000 other neurons. And these neurons fire electrical signals along the axon, and whether this causes another neuron to fire, so whether the presynaptic neuron causes the postsynaptic neuron to fire, depends on whether the synapse is excitatory or inhibitory. And when it comes to neural networks, we can think of these connections or synapses as having a positive weight. If they're excitatory, they have a positive weight, and a negative weight if they're inhibitory synapses. So we'll call this the synaptic weight of the connections between our neurons. Now, for both biological neurons and artificial neurons, if the strength of the signal coming from the presynaptic neuron is strong enough, in other words, if it passes or surpasses the postsynaptic neuron's activation threshold, then that neuron will fire and send a signal to another neuron. So, artificial neural networks are made of populations of artificial neurons. Sometimes they're called perceptrons. Here's a mathematical representation of a perceptron here, where you can see all of the different inputs. There's some mathematical formula in the middle that we'll talk about in just a moment. But basically it takes 4 different inputs, sums the weight of the inputs, determines whether that level of activity is above the activation threshold, and if it is, it outputs a signal to another neuron. So these artificial neurons receive these inputs, which we could represent with a lowercase letter n, which is like the number of a particular neuron, and we assign a numerical value to the weight, that is W subscript I, of each input, I subscript I. And usually this weight is a value between -1 and 1. So positive values here correspond with an excitatory synapse or an excitatory signal, and negative values correspond to a negative signal or an inhibitory signal. And this allows us to calculate the input to our neuron, right? We can multiply each input by its weight, which will give us an activation level for each of those synapses, each of those presynaptic synapses. Then we sum the inputs, which will give us the total input to our neuron. We'll call that x. And if x exceeds the value of our activation threshold, t, the neuron will fire and output a signal, which we call s. So now all we need to do is give our neuron an activation function. So that is what assigns the output signal based upon the input to our artificial neuron. There are many different activation functions. I'm not going to talk about them in detail, but there are some details in the slides. There are 4 different kinds that I talk about in there: linear, threshold, linear, binary threshold, and sigmoidal. I'm not going to go into details about those, but if anyone's curious, let me know, and I can link some good materials for you to read if you want to learn more about this kind of thing. So one of the ways that we can think about what the units in these neural networks do is in terms of computing mathematical functions. So what is a mathematical function? Well, it's something that takes 2 or more inputs and produces an output. So for example, addition is a function. It can take 2 or more numbers, sum them, and produce an output, which is the sum of the numbers that have been added together. So that's a function. We can also talk about mapping functions here. Mapping functions can be helpful when it comes to working out what exactly simple neural networks are doing. So a mapping function, we can understand a mapping function in terms of domains and ranges. So we'll have one set of items that we'll call our domain, and another that is our range. And what a mapping function does is takes certain items in the domain and maps them to one item in the range. And we can actually represent truth values with domains and ranges and mapping functions, as we'll discuss shortly. This is what Gottlob Frege did, who was the inventor of modern logic. Say, for example, that our domain is every natural number. So 1, 2, 3, 4, okay, that's our domain, all the natural numbers. And our range consists of the values true and false. So we want to, depending on how we want to map these numbers, we want to map certain of them to our range of truth values. So a mapping function for the concept of even number would map every even natural number to the value true from our domain to our range, and every natural odd number to the domain of false. So, why are we talking about mapping functions here? Well, mapping functions are important because we can also represent binary Boolean functions using mapping functions, just the way we did with natural even numbers. So, Boolean functions are named after the mathematician George Boole, and binary Boolean functions have pairs of truth values for their domain. So they'll consist of a bunch of pairs of truth values. And of course the values of true and false will form their range. So we might have a domain and a range like this for some binary Boolean functions, where we have false, 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 true, true, false, true, true for our domain. And of course our range is either false or true. So if we wanted to use a mapping function to map out some binary Boolean functions, we would have to map these pairs within our domain to one of the items in our range. So let's look at the Boolean function AND. It maps the value true, and true to true. So it takes true, true from our range, where both of the binary Boolean values are true, and maps it to the value of true, or I'm sorry, it takes that from our domain and maps it to true in our range, and all of the other pairs to false. So we can then say, a function like a and b is true if a has the value true and b has the value true, and our mapping function would take that pair where a and b are both true and map it to true within our range. They would map the other three binary values to false in our range. So if we represented it with a truth table, a handy tool introduced by Ludwig Wittgenstein, it would look something like this, where we have false, 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 true, true, false, true, true. They would all be false except true, true, the last one. So our mapping function is helping us make a sort of truth table here, if you like. Okay, so what the heck does all of this have to do with single layer neural networks? Well, the artificial neurons that I was telling you about earlier, the perceptrons, are basically just computing binary Boolean functions. But they do it with numbers. They use 1 to represent the value true and 0 to represent the value false, of course, as is standard in computer science. And so we can use our artificial neurons to compute these binary Boolean functions. So for example, let's say that we wanted to make something called an AND gate. We could make a single layer neural network, that is a network consisting of a single perceptron, and we could turn it into an AND gate. Say we set the weight of our inputs to 1, and we have 2 inputs, so they both of our inputs have to be true, so they're both firing 1. And we would set our activation threshold for 2, such that if we get true, true as an input to our perceptron, that is 1, 1, our binary Boolean there, our little Boolean tuple, then the network would output a signal because 2 meets our activation threshold. So the neuron will fire if A and B are true, if A and B both have the value of 1. Now, as any computer scientist worth their salt will tell you, modern digital computers are really just like very complicated systems of AND gates and OR gates and NOT gates. And these are all types of logic gates, right? And we can implement all of these functions with artificial neurons. So it seems like they have a lot of potential. But how do the weights get set? Well, usually with perceptrons, this is done randomly, and the perceptron will actually learn to converge upon a solution. So this is really interesting. Now, back in 1943, a couple of researchers named McCullough and Pitts discovered artificial neural networks, and they studied them, but the weights in those networks, so the synaptic weights, the thresholds, activation functions, were all fixed. So these neural networks didn't really learn. But in 1949, a neuroscientist named Donald Hebb came along and published ideas of how learning comes to occur at the neuronal level. Nowadays we call his ideas Hebbian learning, and the basic idea behind Hebbian learning is that neurons that fire together wire together, and neurons that fire apart wire apart. What that means is that the connections between neurons that fire together tend to become stronger, and the opposite is the case with neurons that don't fire together. And this is an example of what we would call unsupervised learning. So the way that a human brain learns and makes these associative connections between neurons is unsupervised, because there's no computer programmer managing the whole thing, right? If we had a neural network that could really do that, that would be perhaps strong AI rather than weak AI. And anyway, Hebb's ideas about Hebbian learning, how learning works at the neuronal level, inspired research on how to make neural networks that could learn to solve problems. Machine learning, basically. So Frank Rosenblatt, who coined the term perceptron, he wanted to find a way to have a perceptron start with random weights and a random threshold and have it learn how to update those weights and thresholds so that it could converge on a solution to a problem. This is what we would call supervised learning, because here the perceptron is given rules that allow it to change its weights and thresholds by a programmer. And moreover, the programmer knows the answer to the problem. The programmer knows the answer that the neural network is supposed to converge upon, and makes sure with training that the network gets there, right? So that's an example of supervised learning. So Rosenblatt came up with an algorithm that would allow perceptrons to do this, and he called it the perceptron convergence rule. And basically, it helps the perceptron to converge upon a solution to a problem by changing the weights and changing the thresholds, so that it reduces error. Basically, we try to get, say, a perceptron to compute a NOT gate, or an AND gate, or any kind of logic gate like this. It doesn't give us the right answer, but we know the right answer. We know what the perceptron would have to be doing to function as, for example, an AND gate. So the convergence rule allows the perceptron to adjust its weights in a step-by-step manner at a specified rate, which we call the learning rate, which allows the perceptron one step at a time to reduce error until error is zero, and it does what we want it to do. Now, I'm not going to talk too much about the details of this, because the math can easily get away from us here. But again, perhaps this is a topic for a future video. If anyone wants to learn about single-layer neural networks, I'd be happy to make a video about that. But anyway, there are certain limits to what perceptrons are able to do, right? Single-layer neural networks, that is perceptrons, can compute AND gates, they can compute OR gates, and they can compute NOT gates. That's because they all share this property called linear separability. But there's one binary Boolean function that is not linearly separable, and that is the XOR function. Now, linear separability is kind of maybe something I should also say for another video, but what I will do is I'll try and find another video or page on linear separability, and I'll link it in the video description in case you want to take a look at that. But basically what this means is that since XOR is not linearly separable, XOR, by the way, is the Boolean function where it stands for exclusive OR, where either A is true or B is true. This is not linearly separable. We can't, well, once you take a look at whatever resources I end up posting, we basically cannot separate the different possibilities, the four different possibilities here on our little graph, and that's what makes this not linearly separable. And all this is to say that single-layer networks can only compute functions that are linearly separable. So what's the problem? Well, Minsky and Papert in a 1969 book proved that the exclusive OR function is not linearly separable and that it could not be computed by a single-layer network. And this kind of put a damper on research into artificial neural networks. Of course, we can compute non-linearly separable functions like exclusive OR by using multilayer networks, by making more complicated networks out of AND gates and NOT gates and OR gates. We can do that, that's no problem. But the problem is that nobody knew how to get multi-layered neural networks to learn. So that was the problem, Minsky's and Papert's book, along with a lack of a learning algorithm that could be applied to multi-layer neural networks. So nobody knew how to train them. We could build them so that they would work from the get-go, but nobody knew how to train them. And that's what's really interesting from the perspective of AI and computer science and machine learning and all of that stuff, is if we could train the multi-layer network to arrive at a solution rather than just program it to work right out of the gate. So, research into artificial neural networks stagnated over about 20 years until the 1980s, when it was really when people really figured out how to train them. And I want to talk about that before we wrap it up today, but first we need to discuss the architecture of multilayer networks. I mean, we've got a pretty good handle on single layer networks, I think, but what about multi-layered perceptron networks? Well, let's take a look at that now. As their name suggests, multilayer networks have multiple layers, and they're built out of lots of individual perceptrons. Specifically, multilayer networks have an input layer, one or more hidden layers, and an output layer. I'll show you a picture of them here so you can have an idea of what they might look like. Of course, I should mention that both single-layer perceptrons and multi-layer perceptron networks are mathematical objects. They're mathematical functions. A single-layer network computes functions. A multi-layer network has lots of little perceptrons that compute functions. There's nothing inherently visual about them, but if we were to try to visualize them, this would be the way to do it. So in a multi-layer network, the individual units are labeled U, or rather units are labeled U, and a particular unit will be U sub I, so we can specify which unit we're talking about by changing that I to a particular number if we like. Units from a previous layer are labeled U sub J, and we can write the weight of a connection between U sub I and U sub J as W sub IJ. And we can of course represent the activation of one of these units with A sub I. Okay? So don't worry too much about all of these mathematical details. It's just a handy way of labeling units in our multi-layer network. Now, we can think of what the multi-layer network is doing like this. The network is computing functions one step at a time in a series of time steps, where n is the number of layers in the network, and information travels from one layer to another in one time step. In the first step, each unit in the input layer will be active. And the activity, or rather the information that's being fed into our network, will be an ordered series of numbers called a vector. And typically, the neural network will have as many input units as there are numbers in our input vector. In the second step, the process is repeated, and the network calculates the levels of activation for the units in the hidden layer based upon the levels of activation from the units in the input layer, which gives us another vector, and so on and so forth through all the layers of the network until we have an output vector. Now, of course, all of the layers, all of the neurons or perceptrons in our input layer, each one of those neurons is connected to each neuron in the next layer, in the hidden layer. But none of the units in the network, none of the units in the input layer are connected to one another. For that reason, neural networks are said to be massively parallel. In fact, sometimes this kind of information processing is called parallel distributed processing, as opposed to symbolic processing. Anyway, that tells us what neural networks are doing from a mathematical point of view, but from an information processing point of view, what are we doing? Well, all of this depends on how we understand the inputs and outputs of our network. So in my Introduction to Cognitive Science class, I often start teaching about neural networks by using the mine rock detector. That was a neural network created by Gorman and Sinowski. And basically it could determine, based on a given sonar profile, whether that sonar profile came from a mine or from a rock. Now, the sonic profiles for these inputs were sampled at various frequencies, and those values were turned into numbers. So each one of those numbers is a number in our vector, and each node in the input layer of that network was responsible for processing that particular number in the vector. So the input vector is like a sonar profile, like a sonic fingerprint, and the idea was the output vector would either output 1, 0, say if it was a rock where, it's rock, mine, 1, 0, that would indicate that it is a rock and not a mine, or the other way around, not a rock, it is a mine, 0, 1. So what really matters from an information processing standpoint, without getting into too many of the nitty-gritty details, is how we encode the inputs and outputs for our network. But to really get an appreciation of what's going on here, it really also helps to know how these networks are trained. How do they learn? How does the machine learning happen here? Well, remember, the reason why research on neural networks stalled for so many years was because nobody knew how to train them. That is until Paul Werbos came up with a learning algorithm called the backpropagation algorithm. He came up with this in the 1970s, I believe, but it was popularized in the 1980s with Rumelhart and McClellan's book, Parallel Distributed Processing, which has a whole bunch of interesting early work that was done with multi-layered neural networks. Now, as the name suggests, the backpropagation algorithm worked something like this. The errors that the network would make were propagated backward through the network once it had finished, a training run. And this error would be used to update the weights and connections and all of that nice stuff of all the units in the network. So why couldn't we just use the perceptron convergence rule for this, rather than coming up with a new algorithm, the backpropagation algorithm? Well, this is the problem when it comes to training multi-layer networks. We know what outputs we want, right? We know the solution. This is supervised learning. We know what we want the network to do given the inputs that we're giving it. So we know what we're expecting. We can have the network do something, and we can even see what the error is between the desired output and the actual output of the network. So we know how to calculate the degree of error, which is important, when the network outputs the wrong answer. But we don't know, based on this degree of error, the degree of error for a given unit in one of the hidden layers, and that's the problem. So we don't know how to adjust the weights of the connections, which is why we can't simply apply the perceptron convergence rule here. But this is where the backpropagation algorithm comes in. The idea of this algorithm, without getting into the nuts and bolts of it, is that it basically, every hidden unit bears some degree of responsibility, if you like, for the overall error in the output layer, or the output vector. The error being the difference between the actual output and the desired output. And this allows us a way to assign a certain degree of error to each of the hidden units, and once we have done this, we can then modify the weights of the connections of the hidden units, their connections from the input and output layers or between other hidden layers. And that, by doing that, we can decrease the error that the network makes until it converges on a solution. It likely won't be perfect, but oftentimes we can train a network like this to do at least as well as a human expert, and oftentimes better than a human expert as well. So the mine rock detector could detect mines versus rocks with much greater accuracy than a human sonar operator could. An important thing about the backpropagation algorithm, and indeed about how information flows through a neural network, activation always spreads forward through the network, from the input layers to the hidden layers to the output layers. But when we apply the backpropagation algorithm, the error is always propagated backward. So activation always moves forward through a network, error moves backward. Thus the weights are updated, and hopefully we're successful at training our network and getting it to output the solution we want, or at least a solution that's close to what we want. Now, as far as the motivation for taking this approach, which is radically different from the symbolic paradigm, well, part of the motivation for studying neural networks like this is that they can actually help us to fill a kind of explanatory gap that we've got when it comes to understanding information processing in the human brain. For example, we have a very good idea of what's going on the large scale in the human brain when we're talking about the level of cortex and different cortices, and we have a pretty good understanding of what goes on at the level of the single neuron or individual neurons. But we don't have a very good idea of what's going on in between that. And neural networks give us a way of modeling and testing models of that level of information processing in the brain. That is to say, that level of spatial and temporal granularity. But obviously there are some pretty big similarities and pretty big dissimilarities too between artificial neural networks and neural networks in the brain. Neural networks, for example, are often homogeneous, so they have perhaps the same kinds of artificial neurons, but there are many, many different kinds of neurons in the brains. Brains are also not necessarily as parallel as neural networks, and while neural networks rarely contain more than 5,000 units, a single cortical column in the brain, which falls into this middle kind of area where we don't have good neuroimaging tools with which to investigate information processing in these areas, well, those cortical columns can contain as many as 200,000 neurons, which is much larger than most artificial neural networks. And there are some other dissimilarities here too. Neural networks, especially the multilayer networks, are trained via backpropagation of error, but there's no evidence that anything like this actually happens in the human brain, right? Neural networks are examples of supervised learning. What goes on in the brain, i.e. Hebbian learning, is unsupervised learning. But all this is to say that what's more important here than all these nitty-gritty biological details is how, on the whole, neural networks process information and how the way they process information differs from how physical symbol systems process information. So, with that said, let's tie it all together. Let's look at some points of contact here and see how exactly physical symbol systems and artificial neural networks differ overall from one another. Alright, so now on to some of the, I guess, differences between these two paradigms, the physical symbol system hypothesis on the one hand and artificial neural networks and parallel distributed processing on the other. Both kinds of artificial intelligence, but they both work in different ways. So remember, on physical symbol systems and the physical symbol system hypothesis, symbols are discrete. We could easily identify them because they're just physical patterns. And the more complicated the information that the symbol or symbol structure carries, the more complicated the symbol or symbol structure is likely to be. And if we took a look at a symbol system from the outside, like if we looked at the tape of a Turing machine, or if we looked close enough at the circuitry of a digital computer, we could identify the symbols, or at least the physical realization of the symbols. We could see the symbols on the tape. We could see the circuits in a computer that could be on or off. That's easy to do. But this isn't necessarily the case with neural networks. That's because neural networks employ a kind of representation called a distributed representation, or a subsymbolic representation. So the representations that a neural network uses are not, strictly speaking, symbolic. Information, that is to say, information in a neural network is not represented in any one specific place in the network. It's represented in the entire network, and all the patterns of activation and weights and thresholds and all of that, what we would call the activation space of the network. So information is represented in terms of all of these different patterns and connections and weights and so forth. This is really interesting because, we could take two identically, at least architecturally identical neural networks, train them to solve the exact same problem, and when we do that, they'd start with random weights and random thresholds, and as we apply our learning algorithm, they'd converge upon a solution, and maybe they would learn to perform exactly as well as one another. Say they both performed at exactly 95% accuracy for, I don't know, doing something like classifying images of dogs versus cats or something like that. So the networks superficially look the same, they perform the same, they do the same task, but if we were to look at the activation space of each network would have a completely different activation space. The patterns of weights and thresholds and all of that stuff would be completely different in each of those networks, even though they both do the same thing equally well. Further, on the physical symbol system hypothesis, information processing is just a matter of manipulating symbols and symbol structures according to rules. And these symbols can be combinations of zeros and ones. They might be well-formed sentences in some kind of logical language. They could even be formulae or sentences in the language of thought, in mentalese, the symbolic language that the philosopher Jerry Fodor thought we think with and think in. Whatever the case, when it comes to physical symbol systems, we can easily distinguish between the rules that operate on the representations and the representations that are operated on themselves, even though both can be represented symbolically. We can't make any kind of comparable distinction between rules and representations in neural networks. Now, neural networks do employ rules of a certain kind, right? We've seen that. The perceptrons use the perceptron convergence rule. Multilayer networks might use the backpropagation algorithm. And of course, activation thresholds are also rule-like. You know, if our input x is greater than threshold t, then output 1. If x is less than t, output 0, right? That's pretty rule-like. But these rules are used no matter what particular problem the network is trying to solve. So whether we're detecting mines versus rocks, or computing Boolean functions, or classifying pictures of dogs and cats, or different handwritten digits, or anything like that, the network is using the same kind of rules. Whereas a symbol system would have a certain set of rules for playing chess, a certain set of rules for playing checkers, a different set of rules for tic-tac-toe, and so on and so forth. So these networks don't differentiate rules in the same way that, that we can differentiate rules in physical symbol systems. Now, neural networks and physical symbol systems can both learn from experience. There are learning algorithms that are symbolic. For example, the ID3 learning algorithm is a great example. I'll post a link to some information about ID3 in the video description. Neural networks are trained, right? That's machine learning too. We like to train neural networks so that they learn how to do things. So they learn from experience. But of course, neither of these systems really experience anything. There's nothing that it's like to be an expert, symbolic expert system, or a neural network that learns from experience, so far as we know. And this will probably become more important in our discussion next time, right, when we start talking about artificial consciousness, whether machines actually experience anything. But for now, keep it in mind for when we move on to that next lecture, our final full lecture on artificial consciousness. All right, so let's wrap everything up now. Well, today we've covered some important concepts like mental representations, regular old representations. We've looked at different kinds of representations like sub-symbolic representations and symbolic representations. We've talked about what computation is, what cognition is. We've talked about the theory of computation and the computational representational theory of mind a little bit. We've talked a little bit about strong versus weak AI, machine learning, and most importantly, we've looked at two kinds of what we could call mental architecture, what Jose Luis Bermudez, for example, calls mental architecture. The architecture of minds, in this case artificial minds, and those are physical symbol systems and artificial neural networks. Next time, we're going to move away from artificial intelligence, now that we've laid the ground with some of these, preparation with some of these fundamental concepts in AI. We'll move on to talk about artificial consciousness and what is different about artificial consciousness from artificial intelligence. And I think what I'll do is kind of walk through the various theoretical standpoints on consciousness and the mind. We'll go through dualism, substance monism, identity theory, the extended mind, all of that stuff. And we'll just talk a little bit about what each of those viewpoints say about whether we could make a conscious machine. And I think I'll wrap things up with a little discussion of how we would be able to tell if a machine were conscious, because we are still faced with this problem of subjectivity, right? Nagel, what is it like to be a bat, all of that stuff. So we'll talk a little bit about the Turing test in the Chinese room and whether we would be able to tell, or how we might be able to tell, whether a machine is conscious. All right, so that's all for today. Thank you again for bearing with me. I know it's taken me longer than is ideal to get this material online, but I really hope you're all finding it helpful. I hope you're all hanging in there. I know this has been a stressful time. I've been talking to a few students, and I get the impression that they're just as stressed out and frazzled as I am. So look, we're all hanging in there. Guys, we're going to make it to the end of the semester, and we're almost there. So stay tuned for my final full lecture on artificial consciousness, and I will see you soon. Bye for now.